A volcanic island in the middle of the Atlantic came much closer to an eruption than most people realized. Not because the sky changed color, not because lava began pouring out, and not because a towering ash column rose from the volcano. The more important signal was hidden underground in a process so quiet that scientists only understood its true scale after carefully reanalyzing the data. Beneath São Jorge Island, part of Portugal's Azores archipelago, a massive body of magma moved upward for more than 20 kilometers below the surface. It did not stop safely deep underground. It did not rise a short distance and fade away. According to new analysis, the magma reached a depth of only about 1.6 kilometers beneath the island. For a volcanic system that is extremely shallow, it was close enough that with just a little more pressure or a slightly different fracture pathway, a new crack could have opened at the surface. The size of this magma intrusion was also significant. Researchers estimate that the amount of magma involved could fill around 3,2,000 Olympic-sized swimming pools. This was not a weak pulse or a minor disturbance deep inside the Earth. It was a large volume of molten rock, powerful enough to deform part of the island, change pressure within fault zones, and trigger thousands of small earthquakes. But what makes this event especially important is not only the amount of magma, it is how quietly it moved. Normally, when magma rises through the Earth's crust, it has to break rock force, open pathways, and create new fractures. That process usually produces earthquakes. These earthquakes are one of the most important warning signs used by volcano monitoring agencies to assess whether an eruption may be developing. The ground shakes more often. Earthquake swarms become denser. The surface may begin to swell. Volcanic gases can increase. In simple terms, the system usually starts making noise before it becomes dangerous. But at São Jorge, the picture was more complicated. The magma rose very high, yet the most important part of that movement appears to have been quieter than expected. The stronger earthquake swarms that caught the attention of residents and authorities may have occurred after the magma had already reached shallow level. If that interpretation is correct, then the earthquakes were not the first warning bell. They were more like a delayed reaction from the crust after the magma had already pressurized the system from below. That changes the way volcanic risk has to be understood. The event first drew major attention in March 2022, when São Jorge recorded thousands of earthquakes. Residents felt the ground shaking. Authorities watched the situation closely because there was concern that an eruption could follow. But in the end, no lava appeared. No ash cloud rose into the sky. No explosion occurred. The island's surface remained intact. From the outside, it looked as if the crisis had simply passed. Only after scientists reconstructed the data more carefully did the deeper story become clear. The volcanic system had come very close to the eruption threshold. Magma had risen from more than 20 kilometers deep and stopped only about 1 mile below the surface. The ground on the island rose by around 6 centimeters. In everyday life, 6 centimeters may not sound like much, but in volcanic geology, that is a serious signal. The ground does not lift for no reason. Something below it has to be adding pressure. Think of a balloon being inflated. Its surface stretches as air is added inside. On a volcanic island, something similar can happen when magma pushes into the shallow crust. Rock is not soft like rubber, but it can still bend, crack, and transfer stress into nearby fault systems. A few centimeters of uplift across a wider area can point to a very large amount of material being injected beneath the ground. To understand why the magma could rise so quickly and so quietly, we need to look. The Azores are not sitting in a simple tectonic setting. This region lies near the interaction zone between the North American plate, the Eurasian plate, and the African plate. As these plates pull apart, slide, and readjust, the oceanic crust becomes fractured in many directions. These fractures are not always visible at the surface, but they create weak zones underground. Magma always looks for the easiest path upward. It does not always rise straight up like a drill. If the rock above it is cold, solid, and unbroken, magma has to use a great deal of energy to create a new path. But if faults, cracks, or weak zones already exist, magma can use those structures as natural pathways. That is one of the key points in the São Jorge event. One important fault zone mentioned in the research is the Pico do Carvão fault zone. This fault may have acted as a pathway for the magma. Instead of tearing through completely solid rock, the magma may have entered a system that was already fractured. That could explain why the upward movement was fast and, at least in its early stages, less seismically loud than expected. But the story does not end there. The same fault system that helped magma rise may also have helped prevent the eruption. Magma contains dissolved gases. When magma is deep underground, high pressure keeps those gases trapped inside the molten rock. As magma rises, pressure decreases and gas begins to separate into bubbles. If that gas remains trapped, pressure builds. That pressure can push magma farther upward, much like pressure building inside a shaken bottle of soda. If the escape route is sealed, the pressure continues to increase. If it becomes strong enough, the system can break through the surface. But if gas and fluids can escape through nearby cracks, the pressure inside the magma decreases. The upward push becomes weaker. The magma may stall before it erupts. That may be what happened at São Jorge. The fault system may have acted both as a highway for magma and as a pressure release valve for the volcanic system. It helped open the way. Then it may have reduced the force needed to finish the eruption. This is why scientists describe the event as a failed eruption. That phrase does not mean the system was harmless. In fact, it means the opposite. It shows that the magma came very close to eruption conditions, but was missing one final factor needed to break the surface. Maybe the gas pressure was not high enough. Maybe the pathway became blocked in the shallow crust. Maybe too much gas escaped. Or maybe the rock above the magma was still strong enough to hold it back. If you are following analyses like this on the channel, take a moment to subscribe and turn on notifications. Not to chase fear, but to understand natural events through data science and calm explanation. Events like São Jorge show that the Earth does not only speak when disaster happens. Sometimes the most important warning signs are found in quiet movements beneath our feet, and that quietness is what makes this case so important. In volcano forecasting, warning time is critical. If magma begins to move and immediately produces mini earthquakes, scientists have more time to evaluate what is happening. Authorities have more time to prepare, residents have more time to follow official updates, check evacuation routes, and avoid dangerous areas. But if magma can move from deep underground into the shallow crust before clear signals appear, the warning window becomes much shorter. That does not mean every volcano can erupt suddenly with no warning at all. That would be an oversimplification. Every volcanic system has its own structure, its own magma source, its own fault network, and its own history of activity. But São Jorge shows one important lesson: earthquakes alone are not enough. A modern volcano monitoring system must combine several layers of data. Earthquakes tell scientists where rock is breaking or where faults are slipping. GPS shows whether the ground is rising, sinking, or moving sideways. Satellite radar can measure surface deformation over a broad area. Gas sensors reveal whether the system is releasing more carbon dioxide, sulfur dioxide, or water vapor than usual. For volcanic islands in the middle of the ocean, seafloor sensors can be especially important because part of the activity may occur offshore or beneath the sea. When all of these data sources are placed together, the picture becomes clearer. At São Jorge, if researchers had looked only at the earthquakes, they might have concluded that the crisis began when the earthquake swarm became intense. But when ground deformation and magma source models are added, the sequence may look different. The magma rose first, stretched the system, and only then did the crust respond with stronger earthquake activity. That is a major difference. For people living on the island, the real risk is not only lava. If a fissure eruption were to occur, lava flows could damage roads, homes, farms, and divide small communities. But even without an eruption, shallow earthquakes can still damage weak buildings, trigger rock falls, destabilize steep slopes, and create long-term stress for residents. Volcanic gases also have to be taken seriously. Carbon dioxide can collect in low-lying areas because it is heavier than air. In places with little wind or poor ventilation, this gas can become dangerous without any clear smell or color. Sulfur dioxide can irritate the respiratory system and affect people with existing health conditions, children and the elderly. That is why gas monitoring is just as important as earthquake monitoring during volcanic unrest. São Jorge is also a volcanic island surrounded by the Atlantic Ocean. If magma were to erupt near the coast or beneath shallow water, seawater could make the eruption more complex. When hot magma comes into contact with water, the water can turn rapidly into steam, causing steam-driven explosions, fine ash, and hazardous eruption column. These eruptions do not always need to be large in volume to be dangerous. If they occur near the coast, they can pose serious risks to residents, emergency crews, and boats in the area. The key point is this: the 2022 event did not lead to an eruption. There is no reason to turn it into a doomsday story. But it should not be dismissed as a small event that no longer matters. In volcano science, near eruption events can be just as valuable as actual eruptions. They allow scientists to see how a volcanic system behaves when it approaches a dangerous threshold but does not cross it. From São Jorge, there are three major lessons. First, magma can follow existing faults, and that can change the warning signals. An open pathway can allow magma to move faster while producing fewer earthquakes in the early stage. Second, a fault is not only a source of earthquakes. In a volcanic environment, it can become a magma pathway, a gas escape route, a pressure zone, or a pressure release valve. Its role depends on the mechanical condition and structure of the crust below. Third, volcano monitoring must be understood as a multi-layered system. No single signal can tell the full story. Earthquakes, deformation, gases, heat satellite data, and seafloor measurements all need to be read together. When one signal is quiet, another may be speaking clearly. São Jorge did not erupt in 2022. But beneath the island, a massive volume of magma rose close to the surface and then stopped. That moment of stopping may have been the difference between a controlled crisis and a real eruption. That is why this event should not be remembered as a warning that failed. It should be understood as a lesson in what volcanoes can do when much of the dangerous movement happens silently. The Earth does not always warn us with explosions. Sometimes it warns us through a few centimeters of ground uplift, through earthquake swarms that arrive late, and through a fault zone that opens just enough to guide magma upward before helping the system release pressure. For volcanic islands like São Jorge, understanding that silence may be just as important as seeing lava at the surface.